Hello students, welcome to the class. In today's class, we will be reading First PUC First Chapter, Some Basic Concepts of Chemistry. This audio book will help you in your revision. So without wasting any time, let us start reading. Some Basic Concepts of Chemistry. Chemistry is the science of molecules and their transformations. It is a science not so much of 100 elements but of infinite variety of molecules that may be built from them. Roald Hoffmann. Science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learnt in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane juice on keeping for prolonged time, and rusting of iron are some of the examples of changes which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure and reactions of material substances is called chemistry. Development of chemistry. Chemistry, as we understand it today, is not a very old discipline. Chemistry was not studied for its own sake. Rather, it came up as a result of search for two interesting things. First one, philosopher's stone, in bracket Paras, which would convert all baser metals, example iron and copper, into gold. Second one, elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and agrochemistry during 1300 to 1600 CE. Modern chemistry took shape in 18th century Europe after a few centuries of alchemical traditions which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and Indian, had their own alchemical traditions. These included much knowledge of chemical processes and techniques. In ancient India, chemistry was called Rasayan Shastra, Rastantra, Raskriya or Rasvidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavations at Mohenjo-daro in Sindh and Harappa in Punjab prove that the story of development of chemistry in India is very old. Archaeological findings shows that baked bricks were used in the construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process, in which materials were mixed, molded and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in construction work. It contains lime, sand and traces of calcium carbonate. Harappans made fanes, a sort of glass which was used in ornaments. They melted and forged a variety of objects from metals such as lead, silver, gold and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Musky in South India in bracket 1000 to 900 BCE and Hastinapur and Taxila in North India in bracket 1000 to 200 BCE. Glass and glazes were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rigveda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BCE. The golden gloss of the black polished ware of northern India could not be replicated and is still a chemical mystery. These wares indicate the mystery with which kiln temperature could be controlled. Kautilya's Arthashastra describes the production of salt from sea. A vast number of statements and material described in ancient Vedic literature can be shown to agree with the modern scientific findings. Copper utensils, iron, gold, silver, ornaments, and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Sushruta Samhita explains the importance of alkalis. The Charaka Samhita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc, the sulfates of copper, zinc, and iron, and the carbonates of lead and iron. Rasopanishada describes the preparation of gunpowder mixture. The Tamil text also describes the preparation of fireworks using sulfur, charcoal, saltpetre, that is potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a reputed chemist, an alchemist, and a metallurgist. His work, Rasratnakar, deals with the formulation of mercury compounds. He has also discussed method for the extraction of metals like gold, silver, tin, and copper. A book, Ras Arnavam, appeared around 800 CE. It discusses the uses of various furnaces, ovens, and crucibles for different purposes. It describes methods by which metals can be identified by flame color. Chakrapani discovered mercury sulfide. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indians began to making soaps in 18th century CE. Oil of Iranda and seeds of mahua plant and calcium carbonate were used for making soap. The paintings found on the walls of Ajanta and Ellora, which look fresh even after ages, testify to high level of science achieved in ancient India. Varahamihir's Brihat Samhita is a sort of encyclopedia which was composed in 6th century CE. It informs about the preparation of glutinous material to be applied on the walls and roofs of houses and temples. It was prepared entirely from extracts of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such material scientifically and access them for use. A number of classical texts like Atharva Veda in bracket 1000 BCE mention some dye stuff. The material used were turmeric, madder, sunflower, orpiment, cochineal, and lac. Some other substances having tinting property were Camplysica, Patanga, and Jatuka. Varahamihir's Brihat Samhita gives references to perfumes and cosmetics. Recipes for hair dyeing were made from plants like indigo and minerals like iron powder, black iron or steel, and acidic extracts of sour rice gruel. Gandha Yukti describes recipes for making scents, mouth perfumes, bath powders, incense, and talcum powder. Paper was known to India in the 17th century, as account of Chinese traveller Ai Sing describes. Excavations at Taxila indicates that ink was used in India from the 4th century. Colors of ink were made from chalk, red lead, and minimum. It seems that the process of fermentation was well known to Indians. Vedas and Kautilya's Arthashastra mention about many types of liquors. Charaka Samhita also mentions ingredients such as barks of plants, stem, flowers, leaves, woods, cereals, fruits and sugarcane for making asavas. The concept that matter is ultimately made of indivisible building blocks appeared in India a few centuries before Common Era as a part of philosophical speculations. Acharya Kanda, born in 600 BCE, originally known by the name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small indivisible particles, which he named Paramanu, in bracket comparable to atoms. He authored the text Vaisheshika Sutras. According to him, all substances are aggregated form of smaller units called atoms, in bracket Paramanu, which are eternal, indestructible, spherical, suprasensible, and in motion in original state. He explained that this indivisible entity cannot be sensed through any human organ. Kanda added that there are varieties of atoms that are as different as the different classes of substances. He said these, that is Paramanu, could form pairs or triplets, among other combinations, and unseen forces cause interaction between them. He conceptualized this theory around 2500 years before John Dalton, in bracket 1766 to 1844. Charaka Samhita is the oldest Ayurvedic epic of India. It describes the treatment of diseases. The concept of reduction of particle size of metals is clearly discussed in Charaka Samhita. Extreme reduction of particle size is termed as nanotechnology. Charaka Samhita describes the use of bhasma of metals in the treatment of ailments. Nowadays, it has been proved that bhasmas have nanoparticles of metals. After the decline of alchemy, atrochemistry reached a steady state, but it too declined due to the introduction and practice of Western medicinal system in the 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It took about 100 to 150 years for Indians to learn and adopt new techniques. During this time, foreign products poured in. As a result, indigenous traditional techniques gradually declined. Modern science appeared in Indian scene in later part of 19th century. By the mid-19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that the chemistry deals with the composition, structure, properties and interaction of matter and is of much use in human being in daily life. These aspects can be best described and understood in terms of basic constituent of matter, that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can we see, weigh and perceive these entities, that is atoms and molecules? Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of these particles? We will get answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical values with suitable units. 1.1 Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain and operation of a computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in big way to the national economy. It plays an important role in meeting human needs for food, healthcare products and other material aimed at improving the quality of life. This is exemplified by the large-scale production of variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides methods for the isolation of life-saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug AZT, that is azithromycin, is used for helping AIDS patients. Chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having specific magnetic, electric and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymers, metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants like CFCs, that is chlorofluorocarbons, responsible for ozone depletion in stratosphere, have been successfully synthesized. However, many big environmental problems continue to be matters of grave concern to the chemist. One such problem is the management of greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical processes, use of enzymes for large-scale production of chemicals and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass, occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living being, etc. are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of states of matter which you learned in your previous classes. 1.2.1 States of matter. You are aware that matter can exist in three physical states, that is, solid, liquid and gas. The constituent particles of matter in these three states can be represented as shown in figure 1.1. Particles are held very close to each other in solids in an orderly fashion and there is no much freedom of movement. In liquids, the particles are close to each other but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. First one, solids have definite volume and definite shape. Second one, liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. Third one, gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. On heating, a solid usually changes to a liquid, and liquid on further heating changes to a gas or vapor. In the reverse process, a gas on cooling liquefies to a liquid, and the liquid on further cooling freezes to the solid. 1.2.2 Classification of Matter. In class 9, chapter 2, you have learned that at the macroscopic or bulk level, matter can be classified as mixture and pure substance. These can be further subdivided as shown in figure 1.2. Matter can be divided into mixture and pure substance. Mixture is further divided into homogeneous mixture and heterogeneous mixture. Pure substances is divided into two categories, that is elements and compounds. When all constituent particles of a substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances which may be present in it in any ratio. Hence, their composition is variable. Pure substances forming mixtures are called its components. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of the components of the mixture are uniformly distributed throughout the bulk of the mixture, and its composition is uniform throughout. Sugar solution and air are the example of homogeneous mixtures. In contrast to this, in heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixtures of salt and sugar, grains and pulses, along with some dirt, are heterogeneous mixtures. You can think of many more examples of mixtures which you come across in daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple handpicking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixtures. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water, and glucose are some examples of pure substances. Glucose contains carbon, hydrogen, and oxygen in a fixed ratio, and its particles are of same composition. Hence, like all other pure substances, glucose has a fixed composition. Also, its constituent carbon, hydrogen, and oxygen cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules. From the previous classes, however, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some of the examples of elements. They are all atoms are of one type. However, the atoms of different elements are different in nature. Some elements such as sodium or copper contains atoms as their constituent particles, whereas in some others the constituent particles are molecules, which are formed by two or more atoms. For example, hydrogen, nitrogen, and oxygen gases consist of molecules in which two atoms combine to give their respective molecules. This is illustrated in figure 1.3. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituent of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Example of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in figure 1.4. Note that a water molecule comprises 2 hydrogen atoms and 1 oxygen atom. Similarly, a molecule of carbon dioxide contains 2 oxygen atoms combined with 1 carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygens are gases, whereas the compound formed by their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is the supporter of combustion, but water is used as a fire extinguisher. 1.3 Properties of matter and their measurement. 1.3.1 Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into 2 categories: physical properties such as color, order, melting point, boiling point, density, etc. and chemical properties like composition, combustibility, reactivity with acids and bases, etc. Physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement or observation of chemical properties require chemical changes to occur. Measurement of physical properties does not require occurrence of a chemical change. The example of chemical properties are characteristic reactions of different substances. This include acidity, basicity, combustibility, etc. Chemists describe, interpret and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. 1.3.2 Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and m denotes meter, the unit in which the length is measured. Earlier, 2 different systems of measurement, that is the English system and metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Late need of common standard system was felt by scientific community. Such a system was established in 1960 and is discussed in detail below. 1.3.3 The International System of Units in bracket SI. The International System of Units was established by the 11th General Conference in Weights and Measures. The CGPM is an intergovernmental treaty organization created by diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in table 1.1. These units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. Table 1.1 Base physical quantities and their units. Base physical quantity, the first one is length. The symbol used is small letter L. SI unit is meter. Symbol is small letter m. Second base physical quantity is mass, represented as small letter m. SI unit is kilogram, which was represented as small letter kg. Third base physical quantity is time. Symbol for representation is small letter t. SI unit is second, and it was represented as small letter s. The fourth base physical quantity is electric current, which was represented as capital letter I. SI unit is ampere. Symbol for SI unit is capital letter A. Fifth base physical quantity is thermodynamic temperature. Symbol for quantity is capital letter T. SI unit is Kelvin. Symbol for SI unit is capital letter K. Sixth, amount of substance. Symbol for quantity is small letter n. SI unit is mole. Symbol for SI unit is small letter MOL. Seventh base physical quantity is luminous intensity. Symbol for the quantity is capital letter I with subscript V. SI unit is candela. Symbol for SI unit is small letter CD. The definitions of SI base units are given in table 1.2. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in table 1.3. 1.3.4 Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. The SI unit of mass as given in table 1.1 is kilogram. However, its fraction named as gram, that is 1 kg will be equal to 1000 gram, is used in laboratories due to the smaller amount of chemicals used in chemical reactions. 1.3.5 Volume. Volume is the amount of space occupied by substance. It has the units of length cube. So, in the SI system, volume has units of meter cube. But again, in chemistry laboratories, smaller volumes are used, hence volume is often denoted as cm cube or dm cube units. A common unit, liter, which is not an SI unit, is used for measurement of volume of liquids. 1 liter will be equal to 1000 ml, 1000 centimeter cube will be equal to 1 dm cube. In the laboratory, the volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare known volume of a solution. These measuring devices are shown in figure 1.7. 1.3.6 Density. The two properties, mass and volume, discussed above are related as follows. Density will be equal to mass divided by volume. Density of a substance is its amount of mass per unit volume. So SI unit of density can be obtained as follows. SI unit of density will be equal to SI unit of mass divided by SI unit of volume. That will be equal to kg divided by meter cube, or we can also write kg meter power minus 3. This unit is quite large and chemist often expresses density in gram per centimeter cube, or also be written as gram centimeter power minus 3, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. 1.3.7 Temperature. There are three common scales to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. Here, capital letter K is the SI unit. The thermometers based on these scales are shown in figure 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degree to 100 degree, where these two temperatures are the freezing point and the boiling point of water, respectively. The Fahrenheit scale is represented between 32 degree to 212 degree. The temperatures on two scales are related to each other by the following relationship. Degree Fahrenheit will be equal to 9 divided by 5 into degree Celsius plus 32. The Kelvin scale is related to Celsius scale as follows. Kelvin will be equal to degree Celsius plus 273.15. It is interesting to note that temperature below 0 degree Celsius, that is negative values, are possible in Celsius scale, but in Kelvin scale negative temperature is not possible. 1.4 Uncertainty in measurement. Many a time in the study of chemistry, one has to deal with the experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. 1.4.1 Scientific Notation. As chemistry is the study of atoms and molecules which have extremely low masses and are present extremely large numbers, a chemist has to deal with the numbers as large as 6022 after that 20 zeros for the molecules of 2 gram of hydrogen gas, or as small as 0.0 after that 23 zeros 166 grams mass of hydrogen atom. Similarly, other constants such as Planck's constant, speed of light, charge on particles, etc. involve numbers of the above magnitude. It may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication or division with such numbers. You can write any two numbers of the above type and try any one of the operations you like to accept as a challenge, and then you will really appreciate the difficulty in handling such numbers. This problem is solved by using scientific notation for such numbers. That is, exponential notation, in which any number can be represented in the form n into 10 to the power n, where small letter n is an exponent having positive or negative values and capital letter N is the number called digit term, which varies between 1.000 to 9.999. Thus, we can write 232.508 as 2.32508 into 10 to the power 2 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and the same is the exponent of 10 in the scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 to the power minus 4. Here the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the scientific notation. While performing mathematical operations on numbers expressed in scientific notations, the following points are to be kept in mind. Multiplication and division. These two operations follow the same rules which are there for exponential numbers. That is, 5.6 into 10 to the power 5 into 6.9 into 10 to the power 8 will be written as 5.6 into 6.9 into 10 to the power 5 plus 8. We will add the powers of 10, so the final answer we will get is 3.864 into 10 to the power 14. Addition and subtraction. For these two operations, first the numbers are written in such a way that they have the same exponent. After that, the coefficients, digit terms are added or subtracted as the case may be. Thus, for adding 6.65 into 10 to the power 4 and 8.95 into 10 to the power 3, Exponent is made same for both the numbers. Thus we get 6.65 into 10 to the power 4 plus 0.895 into 10 to the power 4. Then these numbers can be added as follows. 6.65 plus 0.895 into 10 to the power 4, that will be equal to 7.545 into 10 to the power 4. 1.4.2 significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using the platform balance and it comes out to be 9.4 grams. On measuring the mass of the object on an analytical balance, the mass is obtained 9.4213 grams. The mass obtained is by the analytical balance is slightly higher than the mass obtained by using platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus one which has estimated or uncertain. The uncertainty is indicated by writing the certain digit and the last uncertain digit. Thus, if we write a result as 11.2 milliliter, we say the 11 is certain and 2 is uncertain. And the uncertainty would be plus or minus 1 in the last digit. Unless otherwise stated, an uncertainty of plus or minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. First one, all non-zero digits are significant. For example, 285 centimeter, there are 3 significant figures. And in 0.25 milliliter, there are 2 significant figures. Second one, zeros preceding to first non-zero digits are not significant. Such zeros indicates the position of decimal point. Thus, 0.03 has 1 significant figure and 0.0052 has 2 significant figures. Third one, zeros between 2 non-zero digits are significant. Thus, 2.005 has 4 significant figures. Fourth one, zeros at the end or right of a number are significant provided they are on the right side of the decimal point. For example, 0.200 grams has 3 significant figures, but if otherwise, the terminal zeros are not significant if there is no decimal point. For example, 100 has only 1 significant figure, but 100 point has 3 significant figure, and 100.0 has 4 significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 into 10 to the power 2 for 1 significant figure, 1.0 into 10 to the power 2 for 2 significant figures, and 1.00 into 10 to the power 2 for 3 significant figures. Fifth one, counting the number of objects. For example, 2 balls or 20 eggs have infinite significant figures, as these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal. That is, 2 can be written as 2.000 and so on, or 20 can be written as 20.000 and so on. In numbers written in scientific notation, all digits are significant. For example, 4.01 into 10 to the power 2 has 3 significant figures, and 8.256 into 10 to the power minus 3 has 4 significant figures. However, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value of the result is 2.00 grams and student A takes two measurements and reports the results as 1.95 grams and 1.93 grams. These values are precise as they are close to each other, but they are not accurate. Another student B repeats the experiment and obtains 1.94 grams and 2.05 grams as the results for two measurements. These observations are neither precise nor accurate. When the third student C repeats the same measurements and reports 2.01 grams and 1.99 grams as the result, these values are both precise and accurate. This can be more clearly understood from the data given in table 1.4. Addition and subtraction of significant figures. The result cannot have more digits to the right of the decimal point than either of the original numbers. The additions of 12.11, 18.0, 1.012 will be 13.122. Here 18.0 has one digit after the decimal point and the result should be reported only up to one digit after the decimal point, which is 31.1. Multiplication and division of significant figures. In these operations, the result must be reported with no more significant figures as in the measurement with the few significant figures. 2.5 into 1.25 will be equal to 3.125. Since 2.5 has two significant figures, the result should not have more than two significant figures. Thus, it is 3.1. While limiting the result to the required number of significant figures, as done in the above mathematical operation, one has to keep in mind the following points for rounding off the numbers. First one, if the rightmost digit is to be removed is more than 5, the preceding number is increased by 1. For example, 1.386. If we have to remove 6, we have to round it to 1.39. Second one, if the rightmost digit is to be removed is less than 5, the preceding number is not changed. For example, 4.334, if 4 is to be removed, then the result is rounded to 4.33. Third one, if the rightmost digit is to be removed is 5, then the preceding number is not changed if it is an even number, but it is increased by 1 if it is an odd number. For example, if 6.35 is to be rounded by removing 5, we have to increase 3 to 4, giving 6.4 as the result. However, if 6.25 is to be rounded off, it is to be rounded off to 6.2. 1.4.3 Dimensional Analysis. Often while calculating, there is a need to convert units of one system to other. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. This is illustrated below. Example, a piece of metal is 3 inch represented by IN. What is the length in centimeter? We know that 1 inch will be equal to 2.54 centimeter. From this equivalence, we can write 1 inch divided by 2.54 centimeter will be equal to 1. That will be equal to 2.54 centimeter divided by 1 inch. Thus, 1 inch divided by 2.54 centimeter equals to 1 and 2.54 centimeter divided by 1 inch also equals to 1. Both of these are called unit factors. If some numbers is multiplied by these unit factors, it will not to be affected otherwise. Say the 3 inch given above is multiplied by the unit factor, so 3 inch will be equal to 3 inch into 2.54 centimeter divided by 1 inch. That will be equal to 3 into 2.54 centimeter. That will be equal to 7.62 centimeter. Now the unit factor by which multiplication is to be done is the unit factor which gives the desired units, that is the numerator should have the part which is required in the desired result. It should also be noted in the above example that units can be handled just like other numerical part. It can be cancelled, divided, multiplied, squared, etc. 1.5 Laws of chemical combinations. The combination of elements to form compounds is governed by the following 5 basic laws. 1.5.1 Law of conservation of mass. This law was put forth by Antony Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached to the conclusion that in all physical and chemical changes, there is no net change in the mass during the process. Hence, he reached to the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. This law formed the basis for several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products and careful planned experiments performed by Lavoisier. 1.5.2 Law of definite proportion. This law was given by French chemist Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Proust worked with 2 samples of cupric carbonate, one of which was of natural origin and the other was synthetic. He found that the composition of elements present in it was same for both the samples as shown below. For natural sample, percentage of copper is 51.35, percentage of carbon is 9.74, percentage of oxygen is 38.91, is same for synthetic sample. Thus he concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion by mass. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as law of definite composition. 1.5.3 Law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if 2 elements can combine to form more than one compound, the masses of one element that combine with the fixed mass of other element are in the ratio of small whole numbers. For example, hydrogen combines with oxygen to form 2 compounds, namely water and hydrogen peroxide. Hydrogen plus oxygen to give water. Similarly, hydrogen combines with 2 oxygen atoms to give hydrogen peroxide. Here, the masses of oxygen is 16 grams and 32 grams, which combines with the fixed mass of hydrogen, which is 2 gram, bears a small simple ratio, that is 16:32 or simply 1:2. 1.5.4 Gay-Lussac's law of gaseous volume. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at same temperature and pressure. Thus, 100 ml of hydrogen combine with 50 ml of oxygen to give 100 ml of water vapor. In reaction we can write hydrogen reacts with oxygen to give water, in which hydrogen is taken as 100 ml, oxygen is taken in 50 ml and water produced is 100 ml. Thus, volumes of hydrogen and oxygen which combine bears a simple ratio 2:1. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportion by volume. The law of definite proportions stated earlier was with respect to the mass. The Gay-Lussac's law was explained properly by the work of Avogadro in 1811. 1.5.5 Avogadro's law. In 1811, Avogadro proposed that equal volume of all gases at same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules, which is quite understandable in present times. If we consider again the reactions of hydrogen and oxygen to produce water, we see that 2 volumes of hydrogen combine with 1 volume of oxygen to give 2 volumes of water without leaving any unreacted oxygen. Note that in figure 1.9, page number 16, each box contains equal volume of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If hydrogen and oxygen are considered as diatomic as recognized now, then the above results are easily understandable. However, Daltons and others believed at that time that atoms of the same kind cannot be combined and molecules of oxygen or hydrogen containing 2 atoms did not exist. Avogadro's proposal was published in French journal De Physique. In spite of being correct, it is not gained much support. After about 50 years, in 1860, the International Conference on Chemistry was held in Karlsruhe, Germany to solve various ideas. At the meeting, Stanislaw Cannizzaro presented a sketch of course of chemical philosophy which emphasized on the importance of Avogadro's work. 1.6 Dalton's atomic theory. Although the origin of the idea that matter is composed of small indivisible particles called atomio, meaning indivisible, dates back to the time of Democritus, a Greek philosopher in bracket 460 to 370 BC, it again started emerging as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. First one, matter consists of indivisible atoms. Second one, all atoms of a given element have identical properties including identical mass. Atoms of different elements differ in mass. Third one, compounds are formed when atoms of different elements combined in a fixed ratio. Fourth one, chemical reactions involving reorganization of atoms, these are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination, however, it could not explain the laws of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. 1.7 Atomic and molecular masses. After having some idea about the terms atoms and molecules, it is appropriate here to understand what we mean by atomic and molecular masses. 1.7.1 Atomic mass. The atomic mass or the mass of an atom is actually very small because atoms are extremely small. Today we have sophisticated techniques, example mass spectroscopy, for determining the atomic masses fairly accurately, but in the 19th century scientists could determine the mass of one atom related to another by experimental means. As has been mentioned earlier, hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1 and other elements were assigned masses related to it. However, the present system of atomic masses is based on carbon-12 as the standard and has been agreed upon 1961. Here, carbon-12 is one of the isotope of carbon and can be represented as C12. In the system, C12 is assigned a mass exactly 12 atomic mass unit and masses of all other atoms are given related to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12 of the mass of the one carbon-12 atom, and 1 AMU will be equal to 1.66056 into 10 to the power minus 24 grams. Mass of an atom of hydrogen will be equal to 1.6736 into 10 to the power minus 24 grams. Thus, in terms of AMU, the mass of hydrogen atom will be equal to 1.6736 into 10 to the power minus 24 grams divided by 1.66056 into 10 to the power minus 24 grams. that will be equal to 1.0078 AMU, or that can be written as 1.008 AMU. Similarly, the mass of oxygen 16 atom would be 15.995 AMU. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculations, we actually use average atomic masses of elements, which are explained below. 1.7.2 average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, the average atomic mass of that element can be computed. For example, carbon has the following three isotopes with relative abundances and masses as shown against each of them. Isotope of carbons are carbon 12, carbon 13, carbon 14. Carbon 12 has relative abundance of 98.892, so atomic mass will be 12. Carbon 13 is relative abundance is 1.108 and atomic mass is 13.00335. Carbon 14 has relative abundance 2 into 10 to the power minus 10. Atomic mass will be 14.00317. From the above data, the average atomic mass of carbon will come out to be 0.98892 into 12U plus 0.01108 into 13.00335U plus 2 into 10 to the power minus 12 into 14.00317U, that will be equal to 12.011U. Similarly, average atomic mass of other elements can be calculated. In the periodic table of elements, the atomic masses mentioned for different elements actually represents their average atomic masses. 1.7.3 Molecular mass. Molecular mass is the sum of atomic masses of the elements present in the molecule. It is obtained by multiplying the atomic masses of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains 1 carbon atom and 4 hydrogen atoms, can be obtained as follows. Molecular mass of methane will be equal to 12.011 U plus 4 into 1.008 U, that will be equal to 16.043 unified mass. Similarly, molecular mass of water will be equal to 2 into atomic mass of hydrogen plus 1 into atomic mass of oxygen. That will be equal to 2 into 1.008 plus 16. That will be equal to 18.02 unified mass. 1.7.4 Formula mass. Some substances, such as sodium chloride, do not contain discrete molecules as their constituent units. In such compounds, positive and negative entities are arranged in three-dimensional structure as shown in figure 1.10. It may be noted that in sodium chloride, one sodium ion is surrounded by 6 Cl- ion and vice versa. The formula, such as sodium chloride, is used to calculate the formula mass instead of molecular mass, as in the solid state, sodium chloride does not exist as a single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine. That will be equal to 23.0 U plus 35.5 U, that will be equal to 58.5 U. 1.8 Mole concept and molar masses. Atoms and molecules are extremely small in size, and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote 1 dozen for 12 items, score for 20 items, gross for 144 items, we use the idea of mole to count entities at the microscopic level, that is, atoms, molecules, particles, electrons, ions, etc. In SI system, mole was introduced as 7th base quantity for the amount of substance. The mole, symbol small letter MOL, is the SI unit of amount of substance. 1 mole contains exactly 6.022 into 10 to the power 23 elementary entities. This number is the fixed numerical value of the Avogadro constant represented as capital letter N with subscript capital letter A when expressed in the unit per mole and is called the Avogadro number. The amount of substance, symbol small letter n, of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, any other particle, or specified group of particles. It may be emphasized that the mole of a substance always contains the same number of entities, no matter what the substance may be. In order to determine this number precisely, the mass of carbon-12 atom was determined by mass spectrometer and found to be equal to 1.992648 into 10 to the power minus 23 grams. Knowing that 1 mole of carbon weighs 12 gram, the number of atoms in it is equal to 12 gram divided by 1.992648 into 10 to the power minus 23 grams. That will be equal to 6.0221367 into 10 to the power 23 atoms per mole. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is known as Avogadro constant or Avogadro number, denoted by capital letter N with subscript capital letter A in honor of Amedeo Avogadro. To appreciate the largeness of this number, let us write it with all zeros without using any powers of 10. 60221367, after that 16 zeros. Hence, so many entities, that is, atoms, molecules, or any other particle, constitute 1 mole of a particular substance. We can therefore say that 1 mole of hydrogen atom will be equal to 6.022 into 10 to the power 23 atoms. 1 mole of water molecules will be equal to 6.022 into 10 to the power 23 water molecules. 1 mole of sodium chloride will be equal to 6.022 into 10 to the power 23 formula units of sodium chloride. Having defined the mole, it is easier to know the mass of 1 mole of substance or the constituent entities. The mass of 1 mole of a substance in grams is called its molar mass. The molar mass in grams numerically equals to atomic or molecular or formula mass in U, that is unified mass. Molar mass of water will be equal to 18.02 grams per mole. Molar mass of sodium chloride will be equal to 58.5 grams per mole. 1.9 percentage composition. So far, we were dealing with the number of entities present in a given sample. But many a time, information regarding the percentage of a particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question you would ask is, what is its formula, or what are its constituents, and in what ratio are they present in the given compound. For known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. In other words, one can check the purity of the given sample by analyzing this data. Let us understand it by taking the example of water. Since water contains hydrogen and oxygen, the percentage composition of both of these elements can be calculated as follows. Mass percentage of an element will be equal to mass of that element in the compound upon molar mass of the compound into 100. Molar mass of water will be equal to 18.02 grams. Mass percentage of hydrogen will be equal to 2 into 1.008 divided by 18.02 into 100. That will be equal to 11.18. Mass percentage of oxygen will be equal to 16.00 upon 18.02 into 100. That will be equal to 88.79. Let us take one more example. What is the percentage of carbon, hydrogen and oxygen in ethanol? Molecular formula of ethanol is C2H5OH. Molar mass of ethanol is 2 into 12.01 plus 6 into 1.008 plus 16.00 grams. That will be equal to 46.068 grams. Mass percent of carbon will be equal to 24.02 grams upon 46.068 grams into 100. That will be equal to 52.14%. Mass percent of hydrogen will be equal to 6.048 grams upon 46.068 grams into 100. That will be equal to 13.13%. Mass percent of oxygen will be equal to 16.00 grams upon 46.068 grams into 100. That will be equal to 34.73%. After understanding the calculations of percent of mass, let us now see what information can be obtained from the percent composition data. 1.9.1 Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can be further obtained if its molar mass is known. The following example illustrates this sequence. Stoichiometry and stoichiometric calculations. The word stoichiometry is derived from two Greek words, stoichion meaning element and metron meaning measure. Stoichiometry thus deals with the calculations of masses, sometimes volumes also, of the reactants and the products involved in a chemical reaction. Before understanding how to calculate the amount of reactants required or the products produced in a chemical reaction, let us study what information is available from the balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation for this reaction is as given below. CH4 plus 2O2 giving CO2 plus 2H2O. Here, methane and dioxygens are called reactants and carbon dioxide and water are called products. Note that all the reactants and products are gases in the above reaction, and this has been indicated by letter G in the brackets next to its formula. Similarly, in case of solids and liquids, S and L are written respectively. The coefficients 2 for O2 and H2O are called stoichiometric coefficients. Similarly, the coefficients of CH4 and CO2 is 1 in each case. They represent the number of molecules taking part in the reaction or formed in the reaction. Thus, according to the above chemical reaction, first point, 1 mole of CH4 reacts with 2 moles of O2 to give 1 mole of CO2 and 2 moles of H2O. Second point, 1 molecule of CH4 reacts with 2 molecules of O2 to give 1 molecule of CO2 and 2 molecules of H2O. Third point, 22.7 liter of CH4 reacts with 45.4 liters of O2 to give 22.7 liters of CO2 and 45.4 liters of H2O. Fourth point, 16 gram of CH4 reacts with 2 into 32 grams of O2 to give 44 grams of CO2 and 2 into 18 grams of H2O. From these relationships, the given data can be interconverted as follows. Mass can be interconverted into moles, and that can be interconverted into number of molecules. Mass by volume, that will be equal to density. 1.10.1 Limiting reagent. Many a time reactions are carried out with the amounts of reactants that are different than the amounts as required by the balanced chemical reaction. In such situations, one reactant is more amount than the amount required by the balanced chemical reaction. The reactant which is present in the least amount gets consumed after some time, and after that further reactions does not take place whatever be the amount of other reactant. Hence, the reactant which gets consumed first limits the amount of product formed and is therefore called the limiting reagent. In performing stoichiometric calculations, this aspect is to be kept in mind. 1.10.2 Reactions in solutions. A majority of reactions in the laboratories are carried out in solutions. Therefore, it is important to understand as how the amount of a substance is expressed when it is present in the solution. The concentration of a solution or the amount of substance present in its given volume can be expressed in any of the following ways. First one, mass percent or weight percent. Second one, mole fraction. Third one, molarity. Fourth one, molality. Let us now study each one of them in detail. First one, mass percent. It is obtained by using the following relation. Mass percent will be equal to mass of solute upon mass of solution into 100. Second one, mole fraction. It is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance A dissolves in substance B and their number of moles are Na and Nb respectively, then the mole fraction of A and B is given as mole fraction of A will be equal to number of moles of A upon number of moles of solution. That will be equal to Na upon Na plus Nb. Mole fraction of B will be equal to number of moles of B upon number of moles of solution. That will be equal to Nb upon Na plus Nb. Third one, molarity. It is the most widely used unit and is denoted by capital letter M. It is defined as the number of moles of solute in 1 liter of solution. Thus, molarity will be equal to number of moles of solute upon volume of the solution in liter. Suppose we have 1 molar solution of a substance, say NaOH, and we want to prepare 0.2 molar solution from it. 1 molar NaOH means 1 mole of NaOH present in 1 liter of solution. For 0.2 molar solution, we require 0.2 moles of NaOH dissolved in 1 liter solution. Hence, for making 0.2 molar solution from 1 molar solution, we have to take that volume of 1 molar NaOH solution which contains 0.2 mole of NaOH and dilute the solution with water to 1 liter. Now, how much volume of concentrated NaOH solution be taken which contains 0.2 moles of NaOH can be calculated as follows. If 1 mole is present in 1 liter or 1000 ml solution, then 0.2 mole is present in 1000 ml upon 1 mole into 0.2 mole solution. That will comes out to be 200 ml solution. Thus, 200 ml of 1 molar NaOH are taken and enough water is added to dilute it to make it 1 liter. In fact, for such calculations, a general formula M1V1 equal to M2V2, where M and V are molarity and volume respectively, can be used. In this case, M1 is equal to 0.2 molar, V1 equal to 1000 ml and M2 equal to 1 molar, V2 is to be calculated. Substituting the values in the formula, 0.2 molar into 1000 ml, that will be equal to 1 molar into V2. Therefore, V2 equal to 0.2 molar into 1000 ml upon 1 molar. That will be equal to 200 ml. Note that the number of moles of solute was 0.2 in 200 ml and it has remained the same, that is 0.2, even after the dilution, as we have changed just the amount of solvent and have not done anything with respect to NaOH. But keep in mind the concentration. Fourth one, molality. It is defined as the number of moles of solute present in 1 kg of solvent. It is denoted by small letter m. Thus, molality that will be equal to number of moles of solute upon mass of solvent in kg. Summary. Chemistry as we understand it today is not very old discipline. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge in various walks of life. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter which can exist in 3 states: solid, liquid or gas. The constituent particles are held in different ways in these states of matter, and they exhibit their characteristic properties. Matter can be also classified into elements, compounds or mixtures. An element contains particles of only one type, which may be atoms or molecules. The compounds are formed when atoms of 2 or more elements combine in a fixed ratio to each other. Mixtures occur widely and many of the substances present around us are mixtures. When the properties of a substance are studied, measurement is inherent. The qualification of properties requires a system of measurement and units in which the quantities are to be expressed. Many systems of measurement exist in which the English and the metric systems are widely used. The scientific community, however, has agreed to have a uniform and common system throughout the world, which is abbreviated as SI units. Since measurements involve recording of data which are always associated with a certain amount of uncertainty, the proper handling of data obtained by measuring the quantities is very important. The measurement of quantities in chemistry are spread over a wide range of 10 to the power minus 31 to 10 to the power plus 23. Hence, a convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care of by specifying the number of significant figures in which the observations are reported. The dimensional analysis helps to express the measured quantities in different systems of units. Hence, it is possible to interconvert the results from one system of units to another. The combination of different atoms is governed by basic laws of chemical combination. These being the law of conservation of mass, law of definite proportion, law of multiple proportions, Gay-Lussac's law of gaseous volumes and Avogadro law. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic masses of an element is expressed relative to C12 isotope of carbon, which has an exact value of 12U. Usually, the atomic mass used for an element is the average atomic mass, obtained by taking into account the natural abundance of different isotopes of that element. The molecular mass of a molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. The molecular formula can be calculated by determining the mass percent of different elements present in a compound and its molecular mass. The number of atoms, molecules or any other particles present in a given system are expressed in terms of Avogadro constant. This is known as 1 mole of the respective particles or entities. Chemical reactions represents the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lot of information. The coefficient indicates the molar ratio and the respective number of particles taking part in a particular reaction. The quantitative study of the reactants required or the products formed is called stoichiometry. Using stoichiometric calculations, the amount of one or more reactants required to produce a particular amount of product can be determined and vice versa. The amount of substance present in a given volume of solution is expressed in number of ways. Example, mass percent, mole fraction, molarity and molality. Thank you for watching. See you in the next class.